Okay, so now we're on to our third video here for this last lecture. The third topic is really focusing in on this topic of electrolysis. Okay, I wanted to return to that for a little bit, tell you about some practical applications of electrolysis to make you aware of that as you move forward in your lives and careers. So, in this chapter, we have studied these voltaic cells at some length. We also termed these voltaic cells galvanic cells. Let me zoom in a little bit here so I can write that out for you. A voltaic cell and a galvanic cell are those cells which will operate spontaneously as written. Okay, and basically what I mean by that is the reaction proceeds as it is written, and you get a positive cell voltage for this type of cell. So our prototypical example that we've been considering for some time is over at the anode half cell. We've got the oxidation of zinc. Zinc metal gets converted into zinc aqueous 2 plus ion and a couple of electrons. And then meanwhile, over at the cathode, we got the reduction of something else, and we've been talking a lot about copper. And in that half reaction, the copper 2 plus is reduced to copper metal. So we got the anode, the cathode, and it's set up in just a way that the zinc is oxidized, producing the electrons, which are used to convert the copper 2 plus to copper solid or reduce it. The electrons go from the anode to the cathode. That's the spontaneous reaction, and it generates a positive cell voltage, okay? That's the spontaneous case. Now, what about an electrolytic cell? This is highlighted over here on the right. In an electrolysis cell, we do something very different. First thing I want you to notice is now we're using a power supply or a battery, not the voltmeter anymore. That's necessary in an electrolysis cell. The reason why is because we apply a potential in excess of the native cell potential for the reaction system under study. So here, for the zinc and the copper case, that's going to be in excess of this 1.1 volts. And in providing that excess by the battery or the power supply, we are going to actually drive a reaction to occur. We're going to force a reaction to occur that would not naturally occur on its own. And that's the difference between electrolysis cells and voltaic cells. In galvanic cells or voltaic cells, the voltage is positive, the reaction proceeds spontaneously as written. But in electrolysis cells, we force the opposite non-spontaneous reaction to occur by adding a power supply or a battery and applying a voltage of sufficient magnitude to drive the non-spontaneous reaction to occur. So in the electrolysis cell, what do we have happening? Well, look carefully and closely. This copper electrode is now being oxidized to copper 2 plus. And the reaction which is occurring is that the zinc 2 plus is depositing out as the elemental zinc, or it's being reduced. So we have the opposite reaction. In the electrolysis cell, we force the zinc to deposit and the copper to oxidize because we apply a voltage. So we can run the opposite reaction, the non-spontaneous reaction, the one that doesn't want to naturally occur. We can run that reaction. We just need to force it to occur by having a battery or power supply. And that's basically going to be our nature behind these electrolysis cells, okay? So that's the first thing that I want to kind of get across to you. Now, why are we talking about this business of electrolysis? Why is it kind of useful for us? Turns out it is useful. It's this process of using electrical energy to break a compound apart. And because of that, we can use this for a number of different things. We might be able to take a raw mineral and extract an elemental metal out of it. Maybe we can reduce that metal, for instance. We can produce the element and then extract it, purify it out. Maybe we can produce some hydrogen for fuel cells through the splitting of water. We'll talk about that in a second. That would be a major application for electrolysis cells for the future. And we can also do some metal plating. We talked about that a little bit when we were keeping track of currents and charges earlier in this chapter. We're going to return to an apparatus for that in a second. But these are some practical things that we can do with electrolysis cells. So let's just kind of dive right in. So one thing that I mentioned that I think could be potentially of a lot of potential use in the future is production of hydrogen gas, that's H2, through the electrolysis of water. Turns out we have a lot of water on our planet, don't we? And if we could take H2O and split it up into its elements, that's hydrogen and oxygen, that would be pretty useful. And the main reason why is because hydrogen gas makes a pretty decent fuel. In other words, you can burn it in oxygen or combust it with oxygen to generate heat to an exothermic reaction. You can use that to power devices, cars, planes, so on and so forth. Whatever you want to power with it, really, right? It's an energy source. But the thing is that if we're going to make this work, these fuel cells, well, that wouldn't be really a fuel cell. There's an electrochemical variant of the combustion of hydrogen that would be employed in a fuel cell. But regardless, if we're going to use hydrogen as a fuel most generally, we are going to need to make the hydrogen gas. Now, one option for that, since water is so abundant, is the splitting of H2O into its elements. We can do that with electrolysis. We can run an electrolysis cell. And if we set up that experiment, it would look something like what's depicted on this particular slide, okay? What we would have is a container with water in it and two electrodes, an anode and a cathode. We'd apply a voltage to those electrodes by an external power supply, a battery or a power supply that we would plug into the wall. Okay, now that power supply is not an AC power supply, but rather, generally speaking, it's a DC power supply, direct current, which means it's always on at a constant voltage, and that's actually an important aspect of that power supply, technically. But you apply a few volts, and you can actually get water to split into its elements. Over at the anode, or the anode, of course, at the anode, we got to drive what? An oxidation or a reduction? We have to drive a oxidation. So what is that reaction going to be in the case of electrolysis of water? Well, we take our liquid water and we convert it into oxygen and 4H+. Okay? It's a 4-electron process, 4-electron oxidation. So what's being oxidized here, right? Well, let's take a look at assigning the oxidation numbers. In water, isn't the oxidation number of oxygen -2? But in this elemental form, it's what? 0. So it looks like we've gone from a -2 oxidation state to a 0. It's an increase or an oxidation. Now what's occurring simultaneously over at the other electrode, the cathode? In the cathode, we've got the water being reduced to H2 and hydroxide. Again, if we key in on the key crucial chemistry, the oxidation number of hydrogen in water is +1, but down here it's 0. So it's a reduction. That occurs at our cathode, as usual. So both of those reactions occur in the anode half cell, or also the cathode half cell. And it just so happens in this particular case, we produce either oxygen gas or hydrogen gas. So over here in the anode, we're going to get bubbles of oxygen given off. And that actually flows out of solution, and we can actually collect that in a container. Here it's shown in a balloon, but that could be a tank or something like that, right? And then over here on the right, we have bubbles of H2 being given off. And we can collect that in a container. Now for a fuel cell purpose, or just taking this, putting this in a tank and burning the hydrogen to generate an exothermic reaction, we could collect this up in a tank and then go and use it for energy purposes. But the point is that we have to generate that fuel first by taking our water and undergoing this electrolysis process, whereby it breaks up into its elements. Okay, so this is electrolysis of water. Interestingly enough. All right, so that's one potential application of electrolysis in the future. There's also electroplating. Now we talked about this before, or electrodeposition. I gave you an example problem a few classes back where you had to figure out how much gold deposited on a ring or something like that you were going to buy to see if it was a good deal. So this is kind of what we're talking about with electroplating. What we're going to do here is we're going to make a solution as what's shown here in this beaker. Okay, so this is like a giant beaker basically. And then down in that beaker, we're going to put an aqueous solution that contains metal cations that we wish to reduce and deposit upon a workpiece. Now, in this particular case, it looks like the workpiece or the object to be plated is a little ring over here on the right. Okay, so maybe we're trying to plate some silver onto this ring that's shown on the right. That's our workpiece. Now, in this setup, that workpiece would also be some sort of metal or conductor. And we would basically attach it to a wire that would allow us to shuttle electrons into this half compartment or this object. So we shuttle electrons into that workpiece, and since it's a conductor, they can transfer those electrons to ions in solution. The ions can be reduced through a cathodic reaction, that's a reduction. And in this particular case, we're plating silver plus 1, so the silver plus 1 ion picks up an electron to make silver solid. And guess what? That silver solid that's produced, it will deposit on the surface of the workpiece. We'll plate it out. So what's going to happen is that silver will deposit right directly on that workpiece. And over time, that silver layer will build up. And you can actually coat the entire workpiece and electroplate the silver on that object through one of these setups, okay? Now this is an electrolysis setup because we use a voltage source to apply a potential to make a non-spontaneous reaction occur. Would not otherwise occur. In other words, by applying this voltage source or battery, we force the electrons into that object. We drive them in under a voltage pressor such that the silver plus 1 cation reacts and deposits on the surface. So this is electroplating, okay? Very common electrochemical technique. It's used industrially, obviously, to make jewelry and things like that, okay? We can also purify metals through the electrolysis of molten salts. Now, before we start this discussion, we really need to spend a little bit of time understanding what we mean by molten salt here. This is one example of a molten salt, sodium chloride, but really any ionic compound you could potentially make a molten salt of. Now, here's the thing. When we think of sodium chloride in an experiment like this, you might think that this is a beaker of water with some salt dissolved in it, but that is actually not what we have at all, okay? So I want you to kind of lose that mental model and don't think about that anymore for this particular application, okay? Because here, what we've done is we have heated up sodium chloride to a very, 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 very high temperature to basically melt it into a liquid and make it a molten salt. So notice here in the slide topic, I've got NaCl liquid phase. All right. So what we've done is we've heated up, we've melted the sodium chloride, the ionic compound. They have very high melting points. But if you get it hot enough, you can melt them, you can make them into a liquid. That's what we mean by molten sodium chloride. Now the liquid has very, very interesting properties. Very, very interesting properties. If you melt the ionic compound, you basically start breaking down its 3D crystalline structure, okay? And that has very important consequences because now you've got the sodium cation and the chloride anion, and they basically just start floating around in solution, more or less, okay? Those ions are mobile as they float in solution, so that mixture becomes a conductor of electricity because ions moving is what allows electricity to be conducted. So molten sodium chloride should be a good conductor of electricity, whereas the crystalline solid would not be a great conductor of electricity. So if we melt this sodium chloride, put it in a container, and then we add some inert electrodes, one for the cathode, one for the anode, and we turn on a voltage using a power supply, DC voltage, okay? Always DC voltage for electrolysis. We attach the positive terminal attach to the anode of the battery, and the negative terminal will attach to the cathode. That's where our reduction will occur. If we apply a sufficient enough voltage, we can drive an electrochemical reaction to occur, an electrolysis reaction here. Now, the interesting thing about that is if we drive the electrochemistry to occur, since we've just got this molten salt inside this beaker, and the only thing that's really present in this particular case is sodium chloride, that really limits the possible reactions that can occur. And in this case, since we've only got two possible ions, there are really only two possible reactions. They're listed down here in the bottom. Let's take a look at those real fast. So what could occur in this electrolysis cell? Well, over at the anode, that's where the oxidation occurs. We need to have an oxidation reaction. So what are we going to oxidize? Well, maybe we can take our anion, here that's chloride, and I can add some electrons to make Cl2. Now there's a -1 there. I don't get that, and I don't think that should be there. So I need to cross that -1 out. That doesn't belong there. But what we can do is we can take our chloride in the molten NaCl and react it to make Cl2 gas and a couple of electrons. And that's our oxidation. It's an oxidation because we go from the -1 to the 0 oxidation state. Now over at the other electrode, the cathode, that's where the reduction has to occur. So what can we reduce there? Well, at the cathode, in these molten ionic baths, you take the metal ion and you can reduce it to the element. In this case, also being a 2-electron process. So in the anode, we take the anion and we oxidize. In the cathode, we take the cation and we reduce. But either way, look what we make. We make the element from the salt. So this is actually an interesting way to take ionic compounds and purify them out for their particular elements. In this case, that would be sodium and chlorine, but more generally, whatever elements make up the ionic compound, you can basically purify for. Now, the thing is that in this particular example that we just talked about, we only had one reaction choice for the oxidation and one reaction choice for the reduction. Right? If we look back to it just one more time, right? We said over in the anode, you could take the anion and oxidize it. But then over in the cathode, you had to take the cation, the metal cation, and reduce it. And those were our two processes. And because we only had one salt in this molten bath and nothing else, that's all that really could react. Now, if you set up the experiment that way, I guess it simplifies things for you, right? But the problem is that real life is rarely that simple. Rarely will you only have one reaction that's possible to occur. So we really should reflect upon what happens if I have mixtures present in my electrolytic cells. How will that impact things if I have different ions present? Well, it will impact things. Okay, and I want to impress that upon you, more or less right now. How will it impact things? Well, if more than one cation is present, say in that molten mixture, we had a second cation. What I'm here to tell you is that the cation, which is easiest to reduce, is going to be the one that reacts first at the cathode, and that will continue to react until it's completely consumed. So that's how these electrochemical reactions work. We saw this actually in that last video with the sacrificial anode, like the zinc or the magnesium metal that could protect the iron. And we said that reacts first and it protects the iron, right? And as long as an electrical contact, this works. It's a similar sort of idea, okay? Whatever's easiest to reduce is going to react first. And that's just the way these reactions proceed. Now, likewise, if we have more than one anion present, the anion, which is easiest to oxidize, will react first. Now, these sentences are correct and they're good guiding principles. But kind of on the fly, if you're working a problem, how do you figure out what's easiest to reduce or easiest to oxidize? Well, remember, the position of a particular reaction on our list of standard reduction potentials tells us a lot about the ease with which something is reduced, okay? Because they're listed all as reductions from top to bottom. Things at the top really like to be reduced, things at the bottom don't. So, in terms of easy to reduce, all we really need to do to figure out which possible reaction's easiest to reduce is look at the highest option on our table. Look for the highest option on our table. And once you do that, you're in business, okay? Now, what about for the other reaction? What about the anion? Well, we're told to pick the one that's easiest to oxidize. But oxidation's the opposite process of reduction. So to figure out which one will be oxidized first, you've got to find the lowest option on your table. So to pick which reaction will actually occur, this is our guiding strategy. For the reduction, we pick the highest option on the table, the one that's listed first. And for the oxidation, we've got to pick the lowest option of the table, okay? All right, so let's try to kind of work a sample problem and go through this and see if we can make sense of this, okay? So to help us do this, what I'd like to do is consider this following sample problem. This is going to consider the electrolysis reaction of molten sodium chloride and aluminum fluoride. So sodium chloride and aluminum fluoride. So what I'm here to basically start off by saying is that this electrolysis reaction is really, really, really similar to the one that we saw just a few seconds ago with the two electrodes, and we have an oxidation, we have a reduction, so on and so forth, right? But the thing is that it's not exactly the same anymore because now we've got a mixture. So we have to actually predict what's going to oxidize first and what's going to reduce first. We're going to do a little bit of work. So what I'd like to do is kind of break up our half cell into two compartments, like we would normally do. And then we're going to consider the reactions independently. So in this reaction cell, I've got these molten salts. They're melted down. The ions are, we'll say, freely mobile. So what are my possible options for reduction? Well, one of them is going to be the same that we saw before. Can I add one electron to sodium plus one ion and drive a reduction reaction to sodium metal? I think that's a reasonable thing to potentially occur. But likewise, I could also take my aluminum 3+, add electrons, and make aluminum solid. That's also a reduction. Now, both of those reactions could possibly occur, but one will occur preferentially, of course, the one that's easiest to reduce. And remember, these cells are going to function such that that reaction will continue until you run out of that material, basically, okay? It's almost a selective thing, basically, okay? Or it really is a selective thing. So to figure out which one of these actually will occur, what I think that we need to spend some time doing is looking on our list of standard reduction potentials to figure out where these particular materials place themselves, okay? Now I'm looking at my table here on my brightly colored sheet like the one that I gave to you all earlier this semester, okay? And what I see for my E0 for the sodium reaction is near the bottom, it's negative 2.713, I think. And I also have an E0 value for my aluminum. In my aluminum case, it looks like it's a few entries above at negative 1.676 volts. And both of those are volts versus the SHE, okay? So when I'm looking at this chart, the aluminum reaction is placed above the sodium reaction. And it has a more positive reduction potential. Because of that, I know that if I place those cations in a cell, that the one that's going to preferentially reduce first is indeed my aluminum. That's going to be my reduction half reaction, because it's easier to reduce that. Now what about the oxidation? Well, oxidation is kind of the realm of our anions. So in this case, I've got two anions to possibly consider, the chloride and the fluoride. So it's entirely possible that I take two of my chlorides and or two of my fluorides, and I convert it into the element. These are both gas phase. And in doing that, I'm going to produce a couple electrons in each case. Very similar reactions, just different elements, right? So now I got to ask myself, well, which one is going to undergo this oxidation half reaction preferentially? So if I look up on my table of reduction potentials, I see the very first entry all the way at the top at a positive 2.866 volts. Involves the fluorine. And then I got to go hunting for the chlorine reaction, but it shouldn't be too hard to find it. Let's see if I can come across it. There it is. I think the value is a positive 1.358 from what I'm reading here, if my eyes don't fail me. So these are the values that I get for my individual half reactions for the possible oxidation half reactions in this molten sodium chloride aluminum fluoride bath. And then the question becomes, well, which one will occur? Well, again, what was our guiding principle? For the reduction, we picked the one that was highest on the table, didn't we? But what were we supposed to do for the oxidation? It's the opposite, isn't it? It's the lowest option on the table. So which of these two options were lower on the table? Well, I mentioned fluorine was the top entry, the highest one, the highest reduction potential. So the lowest case is this one. So what's going to happen in this electrochemical cell if we turn it on is the aluminum will reduce out to aluminum solid. And that will happen preferentially over the sodium because it's just easier to reduce the aluminum. So it reacts first. Likewise, in the anode compartment, we'll have the oxidation of the chloride to chlorine gas. And that occurs preferentially because it's easier to oxidize that than fluorine. So simple as that, okay? So we can predict what reactions will actually occur in mixtures. And we've done this now for these molten salts, salt baths, okay? All right, we have a little bit of an extension of work to do on that concept. So I'm going to return to the previous slide, and then we'll be done for the day, okay? Now, I mentioned that the situation gets a little bit hairier, and we just worked a sample problem for if we've got mixtures of ions. Now, in that first sample problem, the mixture of ions that we encountered were for these molten salt baths, and that's it. Okay, just these molten salt baths. The thing is electrochemistry doesn't always occur in molten salt baths. Sometimes we might have aqueous phase experiments. So let's extend our discussion to think about what will happen in these aqueous phases, just really quickly, okay? So what about electrolysis of aqueous solutions and predicting products of those types of reactions? Well, the idea is going to work really, really similar to what we just talked about, okay? The reaction that proceeds as the reduction will always be the highest option on the table, and the reaction that proceeds as the oxidation will always be the lowest option on the table. That's not going to change. But what is going to change is that we are going to have many more possible reactions available to us to consider. So instead of just having, one cation, one anion, or maybe two of each, there can be even more reactions that can possibly come into fold if they're the highest or the lowest option. So let's talk about those. One of the big things that we have to realize is when we do our experiment in aqueous solution or water-based solution, not only can the cation metal be reduced, but it turns out that water itself can also participate in redox chemistry. The water could potentially be the easiest substance to reduce. Now, what is the reaction for water's reduction? Well, it's shown right here. Kind of already alluded to this in terms of these electrolytic cells earlier, but you can take water, add a couple of electrons to reduce it to make hydrogen gas. You also get 2 copies of hydroxide if you do that to balance out the reaction. Now, this particular reaction, under standard conditions, has an E0 cell of negative 0.83 volts for standard conditions. Okay. Now at pH 7, oftentimes this chemistry occurs at pH 7. That standard potential goes to negative 0.41. So again, standard conditions specify what? 1 molar concentration of ions. At pH 7, that's not true, right? We don't have that 1 molar at pH 7. So the cell voltage changes in accordance with the Nernst equation. We learned that earlier today. If you're not at standard conditions, the cell voltage changes, right? So that's why we have 2 different conditions here for that standard reduction potential. But water can potentially be reduced. Now likewise, water can also be oxidized. So when you're thinking about all the different possible anodic reactions, or the oxidations, we could take the element and oxidize it, we could take the anion and oxidize it to its element, like we talked about in the molten salt baths, like with the chloride to chlorine. But you could also take water and oxidize it to O2. And the key and crucial reaction for that is listed right here on this slide. Take a look at that real fast. What do we have? 2 copies of water making oxygen, 4 electrons, and 4 H pluses. And it just so happens that if you look at the voltages for that reaction, actually got to make a correction there and there, that the standard reduction potentials for actually the reverse reaction, where you take the oxygen and you make the water, because that would be a reduction. But those standard reduction potentials are positive 1.23 volts at standard conditions and positive 0.82 volts at pH 7. Okay? So the moral of the story here is the guiding principles are not much different than what we just talked about for the molten salt baths. It's just that we have these other reactions involving water that we need to consider. Maybe water is the easiest to oxidize and or reduce. We need to account for that because water is certainly in our system and it can transfer electrons to be oxidized or reduced. It can participate in this redox chemistry, so we need to consider that. Now, what are some other options? Well, the electrode itself, oddly enough, can undergo redox chemistry. Copper is relatively easily oxidized. It's got a reduction potential of a positive 0.34 volts versus the hydrogen electrode. So copper electrodes tend to oxidize to form that copper 2 plus ion. And you kind of experience this in your natural world as well. If you go see buildings that have copper roofs or parts that are made out of copper, oftentimes after a while, when they're in the air long enough, they'll turn kind of that green-blue color. And that's a clear indicator that copper is present in the metal that was used for the roofing or whatever part that's kind of developing that patina. Now, we don't want our electrode to oxidize, and we'd like to prevent that from happening if there's any way that we can. So we might not use a metal like copper that's easily oxidized. We might use some gold or platinum, something like that, to keep it from reacting because it's harder to oxidize those. Also, graphite electrodes will be a good choice because they don't readily oxidize either, okay? So we can sort of keep the electrode from becoming a problem by a wise choice of what we use for electrode material. Like again, you might want to use gold or platinum, something like that, an inert metal. But know that the electrode could potentially play a role, and it could be oxidized as well. The metal can be oxidized to its ion. So that's something to think about. Now, lastly, another thing to think about is oxygen, gas. This isn't even mentioned on the slide, okay? But oxygen gas, remember when we talked about rusting earlier today? We can reduce oxygen gas. And you say, well, where would the oxygen come from? Well, if you're doing this experiment on the tabletop in a lab somewhere, maybe you've got your electrodes and they're in your beakers. But the thing is that can't gases dissolve in liquids? Sure they can. We learned that in the first chapter of this semester. So we would expect that oxygen gas from the room air could dissolve into our solvent. And if it does, it could react. And it could be reduced. Okay? So there's lots of different options for the potential chemistry that can occur at these electrodes. You have to kind of study the different possibilities, I think, a little bit to understand which potential options are out there. And then beyond that, we just follow these pretty simple rules that we developed up here. The reaction which will occur is the highest option on the table for the reduction. And for the oxidation, the reaction that will occur is the lowest option. And beyond that, there's not much else to it. So I think we'll go ahead and stop here at this point then. And we'll call it a semester since I feel like I'm running out of time for the lecture. But I've appreciated you all to be in this class. It's been great to have you. And I hope to see you all on campus in person sometime soon. Good luck on the final.